Em princípio já está.
Ah, bom. Você sabe mexer? Não. Ó, vídeo. Põe 0.5 para ela pegar essa área inteira. Tá vendo? Tem bloqueio. Quê? E foto também. Tem foto pode pôr um normal. Tem bloqueio? Ah, tá, tem, mas é só fazer isso. Ah, tá pro lado. Ah, não sei, não. Só tá pro lado. Só pra tirar uma foto aí quando a gente vai fazer.
Zé, faz de conta que estás, começa a falar, a fazer de conta que
Tá.
estás a fazer.
Hello everyone, my name is José Osvaldo Filho, and today I'm going to talk about my PhD thesis, which is entitled Stability Design of High-Strength Steel Columns and Beam Columns, and it is under supervision of the professors Luis Simões da Silva, Traiana Tancova, and Hermes Carvalho. Firstly, então deu certo?
Tá bom.
José, mandas uma mensagem quando acabar? Está bem? Tudo bem?
Você tem que sentar na frente. Eu tô brincando. Você me banca. Conversando por
Now we will continue with the Friday at ISISE. And today the presentation will be made by José Osvaldo. And the title of the presentation is Stability Design of High-Strength Steel Columns and Beam Columns. Okay? Good luck.
Hi guys, so as Professor Odina said, my name is José Osvaldo, and today we're going to talk about the most interesting topic in steel structures, okay? Stability. Don't worry, Risa. I'm kidding, Professor Odina. Connections is a pretty good team, okay? So, as Professor Odina said, the title of my thesis is Stability Design of High-Strength Steel Columns and Beam Columns, and it is under supervision of the professors Luis Simões da Silva, Traiana Tancova, and Ernest Carvalho. It's not possible. That's okay. Okay. There we go. So firstly, let's talk about a little bit high-strength steels. As you know, high-strength steels are advantages for constructions, mostly for the ones under heavy loads and with large spans. Sun Center, One World Trade Center, and Shanghai Financial Center are examples of constructions which had been benefit from the use of such steels. But it was not always like that. At the past, the use of high-strength steel was associated with a lot of drawbacks, such as low ductility, low weldability, and low ratio of ultimate to yield strength. With the development of modern steel production techniques such as thermomechanical rolling and quenching and tempering, all these drawbacks were overcome. Nowadays, we know a lot of advantages which can be proportionated by high-strength steels. Reduction in self-weight, smaller foundations, easier fabrication transportation, and low energy consumption CO2 emissions are some of them. Here, I bring the example of the Zandhazen rail bridge, in which the use of grade S4060 was responsible for a reduction of approximately 30% in the self-weight. But as there is this tendency of reduction in the self-weight, there is also a tendency to unstable failure modes and deflections, mostly for compressive members. And the codes we have nowadays can underrate the design because the analytical rules were raised from tests with normal strength steels and not from the tests with high strength steels. As for example, the Oracle 3 design rules have 5 curves responsible to establish the relationship between strength and stability. Each one of these curves is related to a reduction factor. These factors are used to calculate the imperfection. Pode continuar? Tá. So these imperfection factors are used to calculate the reduction factor and then the resistance. The selection of these imperfection factors in these curves are based on the type of the cross-section, if it's welded or rolled, is based also in the strength of the steel and in the geometrical properties. But as we can see here, the same curves are suggested by the Eurocode for the high-strength steel and the normal strength steel. So the main objectives of my thesis are: firstly, validate imperfection factors which were previously proposed by Professor Traiana and Professor Luis Simões for doubly symmetric cross-sections. And the second step is the study of the stability of high-strength steel columns and beam columns with different cross-sections, cover even the monosymmetric and axisymmetric cross-sections, and also non-uniform members with class 4 members. To do that, we developed these 7 tasks here. These first 3 tasks were already done. Here, today, we're going to talk about the development and validation of a finite element model, and also about the parametric study developed with the help of our colleague Felipe Rodrigues. I think he
will present his thesis about the beams, and now we are going to talk a little bit about the columns and beam columns. The task 4, I'm not going to present today because it's under development, and so as we didn't publish anything yet, I'm not going to talk about this. But if you have questions, you can ask me, of course. The task 5, 5, and 6 were not undertaken yet, and the task 7 has been developed along the PhD thesis. So let's talk about the numerical model. The numerical model was validated against the results from the experimental results from the project strobe. In the project strobe, 4 simply supported columns were tested, 2 around the major axis and other 2 around the minor axis. And also 2 beam columns were tested, one hybrid and another one normal. As you can see here, the geometry for both members and supports were represented, the real geometry. Concerning the material properties, the real behavior of the steel was represented by plastic material model with isotropic hardening in Abacus, and the true stress strain curve was also represented. Concerning the mesh configuration, the S4 shell element was chosen, and after a mesh sensitive study, the global size of the element was defined equal to 20 millimeters. So concerning the boundary conditions, their hints were representing by creating a reference point here in the center of rotation of each end section, and these reference points were set as control nodes of all these other nodes here related to the ILETs. So the major axis flexural buckling were able to the columns 1 and 2, and the out-of-plane flexural buckling for the columns 3 and 4. But at the experimental stage, the hints did not work as perfect pinned ends. Actually, it was a transition between the conditions of pinned and pinned fixed ends. As we can see in this image here, the painting is missing, which indicates this unexpected behavior because there was an unexpected contact between these 2 last ILETs here. So the solution was splitting the analysis in 2 to simulate the exact moment where this unexpected behavior occurred. In a first step, there was a first set of boundary conditions, free in plane and out of plane boundary conditions for both ends. And in a second step, there was an imposition of in-plane or out-of-plane rotation at the end section 2, related to the reaction wall of the experimental tests, where this phenomenon happened. As there was also a change of buckling path in the columns 3 and 4. It means that the column were buckling to a side and immediately it turned to buckle to another one. We represented this by the imposition of an inverse direction of the imposed out-of-plane rotations from the previous 3 out-of-plane rotations of the first step. Here we can see that the braces of the columns 1 and 2 were also represented by a third set of boundary conditions, allowing the in-plane rotation and the vertical and longitudinal displacements. At the column 1, also springs were simulated to guarantee that the gaps found at the experimental stage could be represented. In the case of the beam columns, the beam end supports were also simulated as in the case of the columns, and in the shorter leg of the beam columns, there were restrictions of vertical displacements here in this line A, restrictions of lateral displacements in this point C, and the load was applied in this point C. The initial geometric imperfections, which were measured in the project strobe, were also introduced into each node of the numerical models by interpolating the coordinates of the nodes of the numerical models and the coordinates from the scanning system of the strobe, by developing a subroutine in MATLAB. The residual stresses were also measured in the project strobe by the sectioning method, and they were introduced and the partitions previously done in the models. Here we can see the results from the numerical model and the experimental tests. As we can see, for the columns 1 and 2, which buckle around the major axis, the failure modes could be depicted by the numerical model, And also the ultimate loads, the difference between ultimate loads were below 5%. Considering the results for minor axis buckling, we can see that the numerical model could also represent the buckling mode. And do you remember that change of buckling path that I told you before? It also happened in the numerical model, as you can see here. The buckling was occurring to a side, as you can see, and then immediately turned to the other one. Here are the difference between the ultimate load, which are also below 5%. And in the case of the bin columns, the lateral torsional buckling could also be reproduced by the numerical model. And the difference are also below 5%. So after understanding the behavior of the experimental tests, and also after validating the numerical model, we compared the results of the Eurocode and the results of the experimental tests. As you can see here, the results of the experimental tests are above all these curves suggested by the Eurocode, and also the results from the bin columns are above the interaction curve suggested by the Eurocode. We executed also a parametric study with more than 7,000 models. This parametric study, we not can conclude that the Eurocode is safe or not doing this parametric study. We are going to conclude that after the Monte Carlo simulation, where more than 300,000 of models will be run. But now it's just a beginning to understand what Eurocode suggests. As you can see, the study was extended for a major and minor axis flexural buckling with different sections, 45 per sections, normalized slenderness, different ones, from stocky to slender members, and the buckling modes were the in-plane and the out-of-plane. For the bin columns, there was variation in bending moment, as you can see here, and also about the restraints. We simulated members with non-restraints and with minor axis restraint. But to run more than 7,000 models, we needed to simplify the numerical model that I showed before. Concerning the constitutive law, we considered the linear elastic perfectly plastic behavior. Concerning geometric imperfections, we considered the global buckling mode shape with a maximum magnitude equal to the length over 1,000, which is suggested by ISISE. Concerning the residual stresses, the pattern suggested also by ISISE was chosen, as we can see in this image here. So there is, here in this table, we can see the comparison between the results of reduction factor from the numerical model and from using the Eurocode 3. As you can see, the Eurocode 3 is on safe side for this parametric study. It's important to highlight that. But it's, and for the minor axis flexural buckling, it's more pronounced, these conservative results. And as higher as the steel grade, the difference rates. Here, this image is just to illustrate the trend of increasing the reduction factor as higher as the steel grade, which is evident using by the numerical model, but is not even evident using the Eurocode 3. Here are the results of the bin columns. As we can see, the comparison was done in terms of pairs N over M, in which N represents the ultimate load over the plastic resistance, and M, the ultimate bending moment over the plastic bending moment resistance. And again, the Eurocode displays results, conservative results, mostly for the cases where no restraints were applied. And as higher as the steel grade, the difference raises. In these images, we can also see that the results are below the 45-degree line, so which indicates the conservatism of the Eurocode for the results of the parametric study. And so far, we have developed the numerical model, which for understanding the major and minor axis flexural buckling behavior of high-strength steel columns and bin columns. And from the parametric analysis, we can see a clear trend of increasing the reduction factor as higher as the steel grade, which was proportionated by the numerical model, but it was not proportionated by the suggestions of the Eurocode. So adjustment in the rules are required. Here are some outcomes from my work so far. First, there is a paper in engineering structures which is entitled Experimental and Numerical Flexural Buckling, Resistance of High Springs to Columns and B-columns. And you can have access freely, I think, in Science Direct. And the guys from internet, if you don't have access, follow ISISE for more tips. And here is another paper which was presented in CMM. It's in Portuguese, but you can have more details about the numerical model. And here another paper, and you can have more details about the parametric study. It was presented in SDSS last year. And thank you so much for your attention, and I'm open to questions.
Thank you.
Thank you, Professor.
And now, Fernando, it's your turn.
Okay. So thank you for your presentation. Congratulations for your research. That's a very interesting topic. This first one is not actually a question, but a suggestion. You mentioned you did a mesh sensitivity study, but I think it would be nice if you presented, for example, a convergence or.
Let me see where it is. I think I'm almost reaching. This is like.
Yeah. There. No.
Yeah. Here.
There.
Okay.
So I think here it would be nice to present a graph showing the convergence of the results with the mesh size, or present different element types. I don't know.
Yes, thank you. Yes, I'm going to consider the suggestion. I'm going to do that.
Okay. So my second question is, how did you calculate the slenderness for to validate the experimental results? Since the boundary conditions change, as you said.
You mean this graph here? Let me. Here?
Yeah.
Yes. Okay. Yes, it's a very interesting question because I spent a lot of time doing that. Because it's difficult to understand. Firstly, it was so difficult to understand the behavior of the tested columns because they didn't work as pinned ends. So when in Abacus, when we were simulating the boundary conditions, we couldn't reach the ultimate load because, and then even the behavior, it was totally different at the beginning. So we needed to find this by putting springs at the beginning to know which rigidity was working for such case. And then, as we know, the ultimate, the critical buckling load is calculated by p squared IE over the length of buckling squared. This length of buckling can be pinned. It is this length of buckling is equal to the length of the column. If it is fixed pinned, if it's fixed, it is equal to the length is equal to 0.5 the length of the column. And if it's fixed pinned, the length is equal to 0.7 the length of the column. But it was not fixed, and it was not pinned. It was not even fixed pinned as well, because at the certain moment of the experimental stage, it changed. So it was not from the beginning. So it was a transition between 0.7 of the length and 1.0 of the length. So we needed to know which rigidity was that, and to know also the exact moment where this change occurred. So we did a lot of simulations, like thousands of simulations, I don't know the number. And so we solved the case by discovering the spring and also the moment where this change happened, because with this rigidity, we could validate the ultimate load. So a linear buckling analysis was executed after knowing the rigidity. At the boundary conditions, we simulated springs and then executed the linear buckling analysis. And then we could reach the critical load. And then with this critical load, find the correct slenderness and then compare the results. Yes, it was like this. Because if we put like this peanut condition, I think the slenderness should be bigger. Yes. No, smaller. So the results were like here. It was like pretty strange results. So you needed to numerically exploit it, and then change this to know the correct rigidity.
Regarding these Monte Carlo simulations you mentioned you were doing, so are you going to use the same residual stress pattern from the CCS as in the parametric study?
No, because last year Professor Trajana and Professor Wismons with Sharper from German, they developed a new pattern for high-strength steels materials and also for other materials as well. So I'm going to use this new pattern to do the Monte Carlo simulations. Yes.
In your reliability assessment, you also mentioned you were doing, so can you already draw the same conclusions as you had in the parametric study?
So we are developing the analysis until now, but I have some results. Yes, and the results from Eurocode are also conservative for the sections I calculated, but I need to calculate more sections because so far we calculated results with 5 sections. I think more than 200,000 of analyses were already undertook. But as we are like reaching the results yet, I'm not going to conclude it like right now because maybe something can happen with the class 1 section, but I don't think that will be possible because class 1 section there is more resistance on that. So yeah, I think so. Yes.
My last question is also regarding the Monte Carlo simulations. So are you going to use the same imperfections as in the parametric study?
Okay. Global imperfections with the length over 1000, correct? Actually, for the Monte Carlo simulations, we study a lot about the variability of the properties, correct? So we're going to variate the geometrical properties and I think the imperfection as well. But for the imperfections, we are going to create 4 groups. In the first group, they are deterministic, so they are the same one that I presented before. In the second group, they are not deterministic because they are from a they are from a study developed by Fukumoto and Ito. Yes, and yes. But in the third one, they are more recent. There is a recent study that I undertook with Professor Trajano and Wismons, and we collected data and conclude that the statistical parameters should calculate the magnitude of the imperfection. So they will be a little bit different. At the beginning, they are the same one, but after that, we are going to consider another pattern magnitudes, amplitudes. Yes.
That's all.
That's all. Okay.
I have a question. Thank you, José, for your presentation. It was very clear and interesting. I know that you compared with the Eurocode and got like very conservative results from the code, but have you had the chance to maybe take a look at other codes?
No, we didn't do that. We are just consider the Eurocode 3, yes, for this study. Actually, in the paper that I published in Engineering Structure, yes, we consider the Australian code and also the American code. But just to compare with the results of the experimental tests, you know? Yes, so in this paper you can have access of in the results, but like not for the Monte Carlo simulations because it's a lot of Monte Carlo simulations, a lot of simulations. So we are not going to have time like to do the reliability assessment of these codes. But for comparison with the experimental tests, you can have access in my paper, in the paper that we published. Yes.
Do you remember more or less how?
It's conservative as well, but American code is a little bit less than the other codes. And the Australian code is the worst one. It's so conservative. But for the results of the experimental tests, because to do the reliability assessment, we need to have more results. to the raster be consistent. Yes. Okay.
Thank you. More questions?
Thank you for your nice presentation. Actually, I have three questions.
No, this. Okay.
First of all, that boundary condition that you mentioned, for example, pin is pin, both boundary condition. Fix is fix and fix. Pin fix is one boundary condition is pin, the other one is fixed. So if you have rigidity, doesn't mean that it's between fix and pin or so. If one part has like a part of rigidity, the other part as well, you consider pin with rigidity. It's not between fixed pin and pin. This is my opinion.
Okay.
So, because fixed pin is like one boundary condition, totally pin. The other one is totally fixed. That is fixed pin. The one that you have in your case is pin with rigidity. So it's pin with like a slight rigidity in the
Yes, it was, I would like to mean, when I mentioned it, pin transition between fixed pin and pin. We name it like this. Transition between fixed pin and pin. Because it was not pin, and it was not pin fixed. It was a transition, do you know? It's like 0.85, for example. So it was just a name, you know, to explain that, to justify this behavior. But okay.
Because fixed pin is, I mean, in academic words is like one boundary condition, pin, and the other one fixed.
But the other one is not pinned. You know?
Yeah, so
it's not pinned. You cannot say it's pinned.
Okay. No, it's not pin, but it's pin with rigidity. I'm saying pin with rigidity.
Transition between pin and fixed pin. It's just a name.
Okay, but just as a common pin is both pin.
Okay.
Fix is one pin, one fix.
Okay.
It's not about behavior of one boundary condition. And can I see the validity that you have?
Of course.
Yeah, here the second one and the first one.
The second. Okay.
No, that figure.
This one?
No, the other one.
Here?
No, go further.
Okay.
Yeah.
Here?
Yeah. What is the reason of the differences between the initial stiffness?
Okay. It's because in the experimental stage was found a lot of gaps between in the bracings put in the shorter leg of the beam column, for example, and these gaps were responsible for this difference between results. Because in the numerical model, it's perfect, but in the experimental stage, it's not, because of these gaps.
But why the other model has the same stiffness?
Well, because it's different tests. In one, we didn't reach the very good results because there was gaps. But in the columns 1 and 2, for example, in the columns 3 and 4, for example, the gaps did not exist in the experimental test.
And did you get a chance to do a reliability analysis for your?
I'm doing that right now, as I said.
Thank you.
No problem.
More questions?
I think your presentation was very clear.
Thank you, Professor.
Everything.
Thank you so much.
Okay, just I have only one comment following the question of Paul. As you said, that probably it could be the gaps during the experimental analysis.
Yes.
I didn't follow the tests, but normally I associate the gaps at the beginning of the tests, not during the entire stage.
Yes, we justify. There was a question similar to this one from the reviewers of engineering structures, and we justified that the gaps were disappearing when we were applying the load, during the application of the load. So when we reach the ultimate load, and there is no difference between, significant difference between the ultimate load, we could reach that. This here, for example, this difference of rigidity disappeared. But because during the application of the load, the gaps were disappearing as well. It was the justification, and I understood that as well, yes.
Yes, probably because this is a complex structure.
Yeah.
And
It's so complex, yes. It's a 6-meter column, you know. In the literature, we have tests with 2-meter columns made by high-strength steel, welded sections with high-strength steel. So it's a very complex experiment.
Thank you very much.
Thank you, Professor.
I think today we close this session here. Thank you for the presentation.